The oxidation state represents the number of electrons that an atom can gain, lose or share when chemically bonding with an atom of another element. A surprising number of elements can occur in more than one oxidation state, but of particular interest are some of the transition metals, as these can show their change of oxidation state by changing colour. One common element with more than one oxidation state is copper. The 2+ oxidation state is the most common, with its familiar blue colour. The copper-1 compounds are not common. The best known example is the red-brown colour of copper-1 oxide that you see in Benedict's test for sugars. Iron has two common oxidation states, iron 2+ and iron 3+. Here you can see that adding dilute sodium hydroxide to a solution of iron 2 sulfate produces a green precipitate of iron 2 hydroxide. Green is the characteristic colour of iron in the 2+ state. If you oxidise this by adding a small amount of hydrogen peroxide, you will see that it immediately turns the orangish colour of iron 3 hydroxide. This yellow-orange colour is typical of iron 3 compounds. Two of the most interesting examples are vanadium and manganese, which both have multiple stable oxidation states. First, vanadium. Vanadium is most commonly encountered in the laboratory as the 5+ vanadate ion. This is yellow. In this experiment, the vanadate has been reduced all the way down to vanadium 2+ to start with, using zinc. Vanadium 2+ is, as you can see, a rather attractive violet colour. Potassium manganate 7, potassium permanganate, a powerful oxidizing agent, is steadily added to oxidize the vanadium compound. From violet, the solution goes through various blues to the bluey green of vanadium 3, then continues to the clear blue of vanadium 4, before finishing off back at the yellow 5+ again. It is worth pointing out that you will often see a wider range of colours than this simply due to colour mixing. For instance, the solution was green between the blue 4+ and the yellow 5+, but that is simply because it contained both colours, and yellow plus blue when mixed give green. Manganese has even more oxidation states, from 2+ all the way up to 7. There is no single experiment that can show all of them, but this is an interesting and easy demonstration of 3. It is called the colour change chameleon. You prepare a solution of sucrose in dilute sodium hydroxide and then add purple potassium 7 manganate. The purple is characteristic of manganese 7. The solution immediately turns bluish and soon becomes green. This is manganese 6+. The blue colours are simply due to colour mixing. Manganese 5+ is blue, but is not stable enough to manifest itself here. The solution now slowly changes from green to yellow. Now this is interesting, because the yellow is due to nanoparticles of manganese 4 oxide. Manganese 4 oxide is most commonly met as a black powder which is completely insoluble in water. However, these nanoparticles are so small that they remain suspended, and the colour depends on the size of the particles. And even though this is not technically a solution, it looks clear. But if you leave it for 24 hours or so, the manganese 4 oxide particles will settle out to the bottom. You can slow down the reaction by reducing the concentration of sodium hydroxide. This allows a clearer view of the first couple of changes, but then the final change does take hours. It is possible to produce manganese in the remaining oxidation states. Here is a photo showing all 7 of them. Manganese 2+ is the most stable and is a pale pink. Manganese 3+ is less common and a brownish colour. And of the ones we've seen, manganese 4+ is stable, 5 and 6 not very, and manganese 7+ is stable again.